So we're going to be interpreting relations and functions. A relation is not a function. As a matter of fact, let's see, every function is a relation, but not every relation is a function. It's one of those square and rectangle arguments, but you'll figure that out in a moment. So here's our key vocabulary for today. We're going to be talking about inputs and outputs, which we kind of alluded to in our warm-up with domain and range. We're going to talk about the difference between a relation and a function. We're going to talk about various representations of functions and relations. We're going to talk about if a relation is discrete or continuous or neither. Domain and range again, and we're going to do this thing called interval notation. So that gives you a little folder for your brain to put these things in as we start it. Okay, the word function sounds like a scary math term, but it's really not. A function, let me ask you to just kind of ease in here. What is the function of the police force? Okay, stop crying, keep us safe. It's just a job they do, right? What's the function of the school? Teach kids, educate you, whatever. It's a job we do. So basically a function is just a designated job. Okay? So don't think of it as any more than that. It's a machine that has a job to do. So here is a function machine, this little square right here. And basically what happens is I'm going to put something into the machine, and we're going to call it X. We'll say it's a 3. So I'm going to put a 3 into the machine's going to do its job. Where I see an X, put in a 3. Beep, 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 beep. So that means the f of 3, beep, beep, is 3 plus 3 is 6, beep, beep, spits out a 6. So basically you've got an input, which is your X. You plug your X in, and whatever you get at the end is your output, which is your Y. And that can be turned into an ordered pair. The X came in, the Y came out. 3, 6 will be a point on that line. If the next step were to graph that function, it would be a line, and this point would be on the line. Okay? So the job of this function was to take whatever I put in, add 3 to it, and spit out the answer. Now, what you put in has several names, and y'all mentioned them, a few of them. We can call them the input. I'm talking about the thing you put in. Input. We also call that the domain. It's also your X's. And you mentioned all 3 of those in our warm-up today, so that's good. You remember those terminology. What comes out has several names. Give me a couple you think are under here. Okay. Let's see. Output, good. Range. Wise. Ooh, what this is? I don't remember. Oh, it's the dependent variable. So guess what the X is? Independent variable. Yep. Your X is always your independent variable. Your Y is your dependent variable. And what is this? Oh, that was a cover for something else.
Well, I got a question real quick.
Yes.
Okay, so in the function machine, where you get the point 3, 6, how come the right side is the Y?
Because all this means is when I put a 3 into the function, what comes out? So the 6 is what comes out. Am I answering your question?
Yeah, I think so.
You think I did? Okay.
Yeah, I'll think that.
So 3 comes in, 6 pops out. 3 is 6. Okay, here's another thing. Remember how your teachers always told you in the past, if you see an f of x, don't get scared. What can you put in place of that? A y. So I could write y equals 6. Oh, y is this thing. Okay,
Yeah.
that help?
Yeah, I got it.
Okay. And I know it. Oh, that may be us.
It is now time for second line.
Woohoo! Y'all have fun. When we get back. So let's move on here. We are talking about inputs and outputs and all that good stuff. All right. You may be too young, too young to remember this, but do you remember old school texting with this kind of phone where if you wanted to, like dial an A, you push the 1 once? As a matter of fact, get your phones out real quick. Here's an example of, yeah.
And they still haven't texted like that.
Yeah. So, if you were using if your phone had an old school text on it, how would you say hello? What numbers would you push and how many times to make hello? Okay, so old school lines. Okay, so what did you come up with? 4, okay.
3 twice.
3 twice?
5, 5.
Twice.
5.
3 twice.
And then you have to wait a minute.
3 times.
Yeah, you do have to wait a minute. That was always the hard part.
And you have to wait.
Yep.
You have to do 5, 5, 5.
Okay.
And 6, 6, 6.
Oh, I'm gonna take
Whoop,
that.
yeah, 5, 5, 5 again. Okay.
That's ridiculous.
Yeah.
So, if I was doing a domain and range of this function, excuse me, this is not a functions relation, but I'll tell you why in a minute. If you look at all the numbers you pushed, I pushed the numbers, I'm going to put them in order. I pushed the number 3, I pushed the number 4, I pushed the number 5, and I pushed the number 6, right? Okay, the 3, I had to push twice, but it got me an E. Yeah, but if I pushed it another time, so that's all it gave me, wasn't it? Okay. 4, then you H's. Okay, this is another way of putting it. Okay, let's do it this way instead. With a 4, if 4 was your input, how many different outputs, if you used the digit 4, how many different outputs could you get? Right, because you could get either, what are your 3 options?
G, H, I.
Okay, so you could get a G, or you could get an H, or you could get an I. Okay? So, this is an example of a relation, because the 4, you only had one, the input was a 4, but you had 3 different answers, 3 different outputs you could get with that 4. So old time Texas was an example of a relation. Let me show you how this works. Yeah.
We're still recording.
Should be. Am I recording? Yes, I am. Okay, so let's talk about then, so what's a relation, what's a function? Okay, a relation is any time you pair, it's a pairing of input values and output values. Anytime you pair things up, like we did with the texting, you know, the A's were paired up with 3 things. The 1, the 1 there. The 1 was paired up with 3 things. It was paired up with A, B, C, right? I remember mine. No. Oh, it starts with a 2?
Yeah.
Okay. 2 could be an A, B, or C. 3 could be a D, E, F. So anytime you pair numbers, I'm pairing the 2 to the A, the 2 to the B, and the 2 to the C. So, in a relation, you can show it in several ways. You can show it as ordered pairs. So I could write this relation as 2, comma A, 2, comma B, 2, comma C, blah, 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 find as ordered pairs. Or I could do a mapping diagram. This is one that's kind of new. Here's what a mapping diagram looks like. You draw kind of a, whatever shape it is, put the 2 in there, which is your domain. This is all your X's. Your range, you put in another little square, and then you draw arrows to the pairings. So here's the set of ordered pairs that would come out of that, just like I said, W2A, W2B, W2C. Okay. I could also turn these ordered pairs into an equation. I could also graph the equation. And I could also have a verbal model. So the same relation could be expressed in all these 5 different ways. I'm going to talk about those 5 different ways. And we'll also figure out what function is as well. So let's try a couple of these. First, let me tell you what a function is. A function is a special type of relation. Remember I said every function is a relation, but not every relation is a function. So a function is a special type of relation where you only have one output for every input. And it follows three main rules, and I'll give you, actually I'm going to give you a minute to write these down. So as I draw some, keep these rules in front of you and tell me if these are functions or not. Okay? Let's look at this first one. Is the first one a function? Yes. What about this D down here? It's okay. Your number 2 said that some elements in B could not be matched up to A. So it's okay to have some leftovers in your outputs. It's okay. Yes, this is a, whoops. Yes, this is a function. Whoops. Hang on a minute. Come on. Go away. Grab it. There we go. Yes. Okay, look at the second one.
No.
Good, because,
A has to have a-
yeah, everything in here has to have a buddy. You can't have any leftovers in your inputs. Okay? How about this little guy? Good. No, because 1 is matched with 2 different numbers or 2 different letters or whatever.
Is 2 and 3 okay then?
2 and 3 is fine. Yes. Your Y's can repeat. It's just your X's that can't repeat.
They can share the same.
Yes. Yes. Your Y's can share, your X's cannot. How about this one?
No.
No. Because 1 has 2 buddies, an A and a B, and 2 has 2 buddies. Oh, X is 2-timing. X cannot 2-time. Y can 2-time all day long, but X cannot. Okay? This doesn't seem fair, does it? Okay. So, here we go. Let's look at them. Remember, another way you could do it is by ordered pair. Another way you could name a relation is by ordered pairs. So let's look at these ordered pairs and see if these make a relation function. They're all relations because it's pairing of numbers, but are they functions? How about the first one? Yes, because when it's ordered pairs, basically all you're doing is looking at the x's and make sure none of them repeat. So yes, this is a function. How about this guy? No. -8 is triple timing. Bad, bad. Not good for your dating life. Okay, how about here? Yes, it's okay. Remember, the y's can repeat all day long. It's just your x's can't. Okay, so you got the idea about what makes functions cool. So now let's look at it in chart form. So in chart form, is this a function? Yes, again, no x's repeat. This one? No, 7 is 2-timing on us. It's not. How about if it's in graphing form, graph form? Well, in this case, what you do is you use a thing called the vertical line test. You may have heard of this last year in Alpha 1B. The vertical line test you use to see if a graph represents a function or not. And so what you do is you literally draw a vertical line, and if it hits the graph more than once, then it's not a function. So going here, oh, that was a great line, wasn't it? Let's try to actually draw one here with something like this. Okay, that only hit one time. That only hit once. That only hit once. So yes, this is a function. How about a parabola?
Yeah.
Yep. Woohoo! That was so bad. We're pretending those are vertical, okay? How about this guy? No. Wouldn't be prudent. Yes. The x-axis, let me think about that. It cannot hit the x-axis at all. No, because see, this guy hit it twice, and it's the y-axis is what it can't hit twice. Is that what you asked? The y-axis? It's the vertical line it
I
can't
just want to
hit.
get like which line. Like it can only get it once.
Okay, a vertical line cannot go through the graph more than once. The graph itself. So like, let me get a different color here. the graph is this green thing, okay? So when I draw a vertical line, it can only hit the graph in one spot. This one only hit it in one spot. Okay, you got the idea? This only hit it in one spot. But over here, this line hit it here and here. Now let's see why. Why would that make a mess it up and not be a function? Well, think about what this point is. Let's say this is the point, I don't know, what is that? Maybe a 5, 2.5. Let's call it 5, 3. Well, what's this point going to be? 5, negative 3. Look what happened. Be a little x. Did some two-timing on me. Okay? So, use the vertical line test if the relation is in graph form. How about a verbal model? Let's see if these are functions. So first we're going to have to write an equation here. Let's see. To evaluate the f of x, divide the input by 3 and add 2/3 to the result. Okay, first of all, we got to write an equation for that.
X divided by 3 plus 2/3.
Okay, so the f of, and let's write it in function form. So the f of x equals, you're right, we're going to take whatever I put in, divide it by 3, and then do what? Add 2/3. So is that a function? Well, let's see if we can figure out what shape that would be. Can you tell what kind of equation that is? Because couldn't I write that as 1/3 x plus 2/3? Well, that's a fine heavy duty. I think that's a line, right? Will a line with a slope of 1/3, let's think about that. Could I make a statement that every line is a function? There's only one line that is not a function. A vertical line, that's right. A vertical line would not be a function. Let's say this was my, this is so sad, so sad. Let's say this was my function. Well, it's not a function, because if I draw a vertical line right on top of it, it hits it in a jillion trillion places. So a vertical line is the only line that's not a function. And this is not a vertical line. It's a slope of 1/3. So without even graphing it or anything, because of your knowledge of lines and the fact that this has a slope of 1/3, then yes, this is a function. So you got to put all your knowledge together, a lot of stuff of what you know from your past as well. Okay, let's evaluate the g of x. So the g of x, what are we going to do? We're going to take the absolute value of the binomial x plus 2. The absolute value of x plus 2. And then we're going to add 6 to the results. All right, let's think about what shape that is. Remember what shape an absolute value is? It's a V. That's right. Absolute. Surely your teacher has shown you this before. You didn't spell it right. Absolute value makes a V. Well, let's think about V's. Are V's, will they pass the vertical line test?
Yeah.
Absolutely. Absolutely. So as long as the V is facing up or down and not this way, which you're not going to have these at this level of your math class. So yes, this would be a function too, simply because I know what an absolute value looks like.
So absolute values are always functions.
Always V's. Always functions. Yes, ma'am. They are. Whether they open up or down, doesn't matter. You can have a negative in front of that. You can have a 3 in front of that. Makes no difference. It's always going to be a V. All right, now let's talk about this idea of that relations can be either discrete, or they can be continuous, or they can be neither. A discrete relation is when, for example, right here, these 4 points are the only points in that set. If I were to list the points in that set of in that line shape there, help me out up there, Maggie's sister. What is your first name?
Allie.
Allie. Thank you, Allie. Help me out. This is a 2 something. What is that? I can't even see it. What would you think?
Oh. I'm gonna go
You're gonna go what?
8.
8. Okay. And then let's go -1, maybe 6. And let's go negative 4-ish. Okay, that's close enough. Negative 5, 4. And last one is negative 8. 2. Okay, so the only members of this domain, the x's, are 2, negative 1, negative 5, and negative 8. Those are the only members of your domain. Nothing in between, just 2, negative 1, negative 5, and negative 8. And your range is just 8, 6, 4, and 2. So these are called discrete because they're just points. However, what if I were to connect the points? Well, if I can connect them, then it's a continuous function. One thing, because it looks continuous. You never lift your pencil. Once you start, you never lift it. But let's think about what that means, too. That means that negative 1 has a value, negative 2 has a value, negative 3 has a value, negative 4, negative 5, negative 6, negative. There's a whole, and even negative 1, let's see, what is that, negative 2, yeah. Negative 2 and a half would have a value. Negative 2 and a fourth would have a value. Negative 2 and a third. I mean, every single cotton picking x you can put in there is going to have, at least between here and here, every x is going to have a value. So it's continuous. Now this one is neither, because watch what happens. Yeah, it's continuous between here and here, but then you have to pick up your pencil and move down. So it's not continuous because you have to pick up your pencil. And it's not discrete because it does have a whole bunch in between here. It's not just dots. So let's be neat. Okay. Makes sense, I hope. Is it some of this? So the domain, as we said, it's the input values. It's an independent variable. The range is a set of output values. It's the dependent variable. So if I said give the domain and range for this relation, what's the domain of this relation? The x's. 1900, 1920, 1940, 1960, 1980, 2000. And the range? 2, 3, 4, 15, and 33. So is this discrete or continuous? Are we measuring any years between 1900 and 1920? It stayed the same. It stayed the same between 1900 and 1920. Well, first class stamp rates. Let's think about that again. Let me think about that. Yeah, you could. Yeah, because time would have in between. Yeah, so it would be continuous. Because there is a 1910 and a they just chose to pick a point every once in a while. Yeah. Okay. So now let's look at in graph form. We're going to tell the domain, we're going to tell the range, we're going to tell if it's a function or not, and if it is a function, tell if it's discrete, continuous, or neither. All right, here we go. By the way, when you write just the domain or range, you put it in braces because it's a set of numbers. So what is my domain here? Well, looks like I've got a negative 3 something. Looks like I have a negative 2 something. Looks like I have I've got a 1, double. You do not repeat your numbers when you're listing domains and ranges. Even though the 1 is used twice, don't write it twice. Just write it once. Oh, I didn't see that little guy. He's hiding. Yes, and a 4. Okay. And the range. Give me the range. Negative 4. 5. Negative 2. All right. So, is it a function? No way. No way, Jose. Because a vertical line right here, boom, boom. Hit it twice. Okay, so no function. However, it is a relation because it's a pairing of numbers. Is it discrete, continuous, or neither? Discrete. Yep, very good. Discrete. single look of my.
So you can classify it as discrete, continuous, and relative.
Yep. All relations can be discrete or continuous.
Okay.
Yep. All right, interval notation. Let's talk about that. Because when we look at this domain, because this is continuous, I can't list every point between, like if I were to start listing the domain, I'd have to list -3, -2.999999, -2.99998, -2.99997. I mean, I'd be listing them all day. Okay? So what I'm going to do instead is I'm going to write this in interval. Think about what an interval means, a set of time from 6 to 5 or from 2 to 10. Okay, intervals. So I'm going to write this as an interval then. The domain is going to be every number between what is that, a -3, comma, and it's going to go all the way out to a +3. And I'm writing it in braces because it is including this point and this point. It includes the -3 and the 3. If those were open dots, like we graphed at the beginning with our open dot, then I would have put parentheses. Did y'all do interval notation in Algebra 1B? No? So this is new to you? Okay, I wasn't sure. Some teachers do teach it that way. So now let's look at the range. Okay, my set of y's. And you want to go, whenever you mention domain, go from left to right. When you're talking about range, go bottom up. Okay? So the domain, again, this is my lowest range, which would be a is that a 4?
4.
So -4, comma, goes all the way up to a +3, and every number in between. So that's why I'm going to use interval notation. Is this a function? No, not at all. Is it continuous or neither? It's, yes, it's continuous. Because it has every point in between. Notice how domain and range are an interval of numbers, so we use interval notation. Yes, I did notice that. Okay, so let's practice this interval notation business. This is how we did it in pre-algebra. If you had x was less than or equal to -2, remember we did an open, no, that would be a closed circle at 2, that's not a -2, and we would do to the left, right? Well, we're not going to do that anymore. Now we're big boys and girls. So, how far does this go to the left? To infinity. Actually, to -infinity. However, you never reach infinity. Therefore, you always put a parenthesis when you're talking about going to infinity or -infinity, because you never really reach it. I know it's kind of weird. And at 2, though, it's including 2, so we're going to put a closed bracket there. All right, when we just had x was less than 2, that would have been an open circle in pre-algebra going to the left, right? So we're still going to -infinity, still with a parenthesis because it never reaches it. What am I going to put after this 2? A parenthesis, because it cannot be 2. It can go right into 2, but not catch it 2. All right, x is greater than or equal to 3 would be colored in going to the right. What do you think? Bracket, 3. Infinity, now we don't need to put plus. When you don't put anything, it knows it's positive. And parentheses, because you don't need positive infinity either. So you get the idea? Greater than 3. So that would be parentheses, 3, infinity, parentheses, good. Ooh, what's this in between business? Well, this is what we would have done. We would have had, okay, we've got a 4 and a 10. So in probably algebra 1, it's probably not pre-algebra, but I would have had an open circle here, I'd have had a closed circle here, and it would have been everything in between. All right, so let's write that in interval notation. So, beautiful. Ooh, what about this? Less than -2 and greater than or equal to 5. Oh, well, I've got to write two different statements. So let's just describe this one first. Mm-hmm. Yes. So it's from -infinity to 2, and then we stop. And we're going to use this symbol, which means in union with. And now we're going to write this. Beyond. Make sense? Kind of fun? I like interval notation. So from now on, you will be using interval notation whenever you describe these inequalities throughout the rest of the semester, and in analysis and calc and all that too. It's the grown-up way to do it.
It is now time for fourth lunch.
I was going to say, it better not be time for this class to be over, or we're in deep duty. Oh, I said that. 4 lunches, yes. Yeah, really. Okay, now, what if we have this? Okay, now that we know what interval notation is, let's go back to this. So my domain then on this guy is going to be, give me interval notation. Bracket or parenthesis? Parenthesis? Uh-huh. Ooh, wait a minute. This has an arrow on the end. Infinity, and we never reach it. How about the range? What's the lowest I'm going? Okay, a +1 is the lowest I'm going to go. Ooh, but those are both filled in. So that's actually going to be a bracket there. From 1 to infinity again. Because now it's going up to infinity. It's going to the right to infinity, but it's also going up to infinity. Yes, sir.
Just one be filled in on this?
Just one be filled in.
On the range of them.
Yes, this could be open and that could be closed. If one was open, then it would not be continuous, but you could still. Oh no. Then your range would you'd have to describe from this point to there. Let's say this was open, so you'd have to describe from here to here, and then do in union with from here to here. Yeah, good point. That'd be tricky. So is it a function? Yes, indeedy. It is good, and it would be continuous. Okay. Oh, what about circle? Give me the domain. There you go. Feel free to join in. No. Domain. Now domain is your x's. This is going to go to the left forever and to the right forever. There you go. -infinity to infinity. Range? Yeah. Function? Continuous, right?
Yep.
All right. You're doing great. Domain? Very good. Yep. Whoa.
Look out.
Sorry about that. Function? All right. Domain? Range? Careful. That's right, because this is going to go down forever and up forever. Function? Okay, well, yeah. Okay. The domain, let's think about that. Well, I'm gonna be at negative infinity, that's for sure, right? Yeah, but does one, but one has a function. I mean, one has a point on it. So it's not gonna be continuous. It's not continuous, because I have to pick it up. It's not discrete, so it's neither. But as far as the x's, it's from negative infinity to infinity. Because there's no holes in my graph. There's a point at 1. Now 1 has 2 values, so it's not a function. And no, it's not a function. But every x has something correlated with it. Yes, sir.
So like it can overlap. Like okay, so in the top graph is moved over to 1. So that points at like -2, and the other one's at 1 or -1.
So it was like this.
Yeah, that's what I'm saying right there.
Okay.
So like, is it still negative infinity?
No. Oh, yes, it would, because this point right here covers your -2. Even though it's open here, -2 is covered by this.
Okay.
So if it's like -1 and 0.
So like if this point started instead of here, pretend that wasn't there, and this was here, then I'd have to use a union, because there is nothing for the x's between 0 and -1. There's no y's associated with any of those x's. So I have to have a union in between those. I think I have one of those. Hang on, let me see. Yeah, okay, let's do this one. Oh, don't forget the range. Oh, interesting. The range is only going to be 2 numbers. 1, 3.
Wouldn't it be backwards?
Yeah, it wouldn't be
No. You know what we've got to do? We've got to go 1, union 3. Because it's not in between them. It's just 1 and just 3. That's the only thing we got. That's weird. That's weird. I'm glad you made me go back to that. They're going to get weirder. The more you go, the weirder they get. Okay, let's look at this domain. Obviously, it's going to go from negative infinity. Does the x value -3, does it have any partners? No, there is no value at -3. So I've got to write this as 1 in union with this. So I'm going to go from negative infinity to -3, but not including -3, so it's a parenthesis. In union with not including -3 to 2. Not including 2 because it's an open circle. I kind of think it through, huh? Yeah. Okay, range. My y values. What's the lowest y I've got?
-2.
Good. And do I have something at -2? Yeah. So -2, 2.
Oh,
No, because we're talking up. We're not talking to the left, we're talking up. Because we're talking the y values. So it would be positive. Function? Yep. Continuous? Nope. Discrete? Nope. All right. Oh, yes.
wouldn't it not work because there's an opening?
There is an opening, however, 2 has a value, because 2 has a value right here. Every number has, every y has an correlating x. 2 has a correlating x right here. Everything has a correlating x, because we're thinking up and down, not left and right. Give me an example. Where would you think there's not a where would you think there's a hole or a problem?
-3, -2.
-3, -2. Okay. -2 is a y value, right? So you're thinking there's no x to go with it. But there really is, because 0 goes with -2.
So as long as there's, as long as one, the, line is, I have no idea how to explain it.
As long as there's some x somewhere on the graph to go with every y, that's what you're looking for. That's the question you're asking. And when you're looking for domain, you're asking the opposite question. Is there some y for every single x? Okay? So, kind of weird, kind of fun. Let me turn this